On this video, we're going to go through a couple more examples utilizing what the derivative, both the first and the second derivative actually, tell us about a function's graph and use that information to give us some rough sketches of the graphs of a couple functions. So let's start off with this one. I call these formula graphs or choose your own graph, like choose your own adventure graph, where you've got information about the function and you have to generate a graph that would satisfy these conditions. So not everybody's graph is going to look exactly the same, but the graphs do need to meet these criteria. So what are we going to do with this information? Well, the first thing that we're told is that the function is continuous. So when we get done, we better be able to trace our curve without ever lifting up our pencil. So this function is continuous. We are also told in the first line just some ordered pairs, basically. We know that f of 0 is 7, f of 5 is 0, and f of 10 is 11. So just getting started, I'm going to go ahead and plot those. So we've got, let's see, 7 would be right here. So f of 0 is 7. So the graph will pass through that point. F of 5 is 0. The graph will pass through that point. And f of 10 is 11. So the graph will pass through that point there as well. So we will go through those 3 points. We are also told that the limit of the function as x goes to infinity is 0. So if the limit goes to 0 as we approach infinity, I'm going to do this kind of in red. We know that at some point out here on the graph, now we need more information, so I'm just going to kind of sketch in. We know it's going to be one of these. Now, of course, that can't be both of these because this would not pass the vertical line test, so we can't have both of those graphs, but I'm just going to put some little arrows there to remind me that when I get done, my graph does need to approach. As I grow without bound on the x-axis, my function is going to approach 0, be approaching the x-axis. Okay, now we have a bunch of information right here about the first derivative. So what am I going to do with that information? So I want to zoom in on that information for a second so we can see it. It was getting a little small for my eyes right there. So if we zoom in, we are told that the derivative is equal to 0 when x is equal to 0 and 10. Well, what does that mean? What does that tell me about the function? That means those are places where I have a horizontal tangent. It is also giving me some critical points. So I'm going to list some critical points down here. So it's also telling me, because that's by definition what a critical point is, it's places where the derivative equals 0 or is undefined. So we know that 0 and 10 are critical points. This second piece right here is saying that the derivative is undefined. So if the derivative is undefined, it could be that we have a vertical asymptote or a corner or a cusp. Well, I can eliminate the vertical asymptote because the function is continuous, meaning I can draw this function without ever lifting up my pencil. So that means at 5 we must have a corner or a cusp. We'll utilize that when we get into the actual graphing, but I could cross off that option of a vertical asymptote. So I'm going to go ahead and say that x equals 5 is also a critical point, because remember, critical points come from the two places, just a quick note, right? Our critical points are when the derivative is equal to 0 or when the derivative is undefined, right? So kind of my little thought bubble. My critical points are those places where the derivative is either equal to 0 or undefined. Okay, so once I have my critical points, I could make a sign chart, and I want to make a sign chart. It's going to help me to graph this. If I know where the function's increasing and decreasing, I'll be able to graph this a little easier. So I'm going to use a sign chart because it's just a lot of information about the derivative. So we have to organize it somehow, either with a sign chart or in our heads. It's a lot to kind of keep track of in our heads, so I'm going to organize it on a sign chart. We were not given any restrictions on the domain, so I'm not going to restrict my sign chart here. We're going to take a look at the sign of the derivative. So just as a reminder, we did a couple examples of these in some previous videos, but a sign chart for the derivative is going to tell me where the function is increasing, where f of x is increasing or decreasing. So looking at the sign of the derivative on the top of this line that's representing our x-axis will give us some information about whether the function itself is increasing or decreasing. So when we make a sign chart for the derivative or the second derivative, we use the critical points from the derivative or the second derivative to break it apart. Well, that's why I listed them out here. So we've got 0, 10, and 5. They're a little out of order there, so I'll make sure I put them in order. So we've got 0, 5, and 10. Those are the places where the derivative is either equal to 0 or undefined. Now I'm just going to start filling in. This says that the derivative, so on the next line now, it says the derivative is greater than 0, which means positive. So the derivative is positive from negative infinity up to 0. So if the derivative is positive, that means that the function is increasing on that interval. Then we know at 0 that we have a horizontal tangent line because we were told that. So we know that f prime of 0 equals 0, which means we have a horizontal tangent line. I'm just going to put that note down below here. Then we keep going. Then we're told that the derivative is greater than 0 also from 5 to 10. So from 5 to 10, we also know that the function must be increasing from x running from 5 to 10, so along x being from 5 to 10. We also know that at 5, we don't have a horizontal tangent. We know that f prime of 5 is undefined, which, because we also know we have a continuous function, we know that that's going to be a corner or a cusp. Then we know the very last line here says that the derivative is less than 0 from 0 to 5. So the derivative is negative. Less than 0 means negative, which means it's decreasing on that interval. And then we also know that it's decreasing from 10 to infinity because the derivative is negative. So it's also decreasing there. We also know that 10 is another place where we have a horizontal tangent. So we know that f prime of 10 is equal to 0, which means we have that horizontal tangent. That's what those mean. So now I can take that information, kind of looking at this information, I know that the function is increasing, right? I'm going to get a very nice solid graph over on the graph, but before I even do that, before I walk away from the sign chart, I know that my function is increasing until it gets to 0. Then it has a horizontal tangent. So that means it must have something, it must have some behavior like this where it hits that horizontal tangent and then it begins to decrease. It decreases until it gets to 5. I need to make my graph a little bit wider there. Decreases till it gets to 5. And then it starts to increase. It has to be a corner or a cusp because the derivative is undefined. So I couldn't curve that like this because I know the derivative is undefined. It doesn't have a horizontal tangent line. So it had that horizontal tangent line at 0, but it has a corner or a cusp at 5. Then it's going to start to increase until it gets to 10. When it gets to 10, it again has a horizontal tangent line, something like that. And then it goes down. So I know that this is the general shape of my graph. I know that these must also be maxes and min and max, simply because we're going from increase to decrease, that generates a max. We go from decrease to increase, that generates a min, and then we go from increase to decrease, and that generates a max. So I know all of that just from the sign chart. With the other little pieces of information about the continuity and the limit that we're given, I can now come over to my graph. I'm going to shrink this down a little bit so I can get the whole graph on the screen here. If I shrink that down a little bit, I get that whole graph on the screen, and now I can actually start to plot. So I know that as I go from negative infinity to 0, I'm increasing. So I'm going to have a shape that looks something like this. Again, everybody's graph is a little bit different. I'm also had those ordered pairs that I'm going to go into, so I know I'm increasing. I know at 0 I have a horizontal tangent. I also know at 10 I have a horizontal tangent, so I could put those lines in to give me kind of some guidelines. I know that at 5 I have a corner or a cusp, as we already discussed, and so this is then going to come down, comes down sharply, hits that point, the derivative is undefined, and so then I would go up, 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 hit that point at 10, 11, and then I'm going to come down. Now the other piece that was given was that I also have to approach 0 as x approaches infinity. As x grows without bound, I'm also going to head out to the graph of my function is going to approach 0. So I'm going to extend my graph just a little bit, and I'm going to get that piece in there a little nicer. So I'm going to come down, really show that limit approaching 0. And now I can get rid of some of my other little pieces on here. I know that if I wanted to, I could label, I've got a local max, a local max. I got 2 local maxes. I got a local minimum. I'm a continuous function, and I satisfy all of the criteria. So that sign chart sort of helps us to get all that criteria. We had that general shape of the graph underneath the sign chart, and then we cleaned it up by using the plotted points and the limit that was given and the fact that we had continuity. So knowing that with that continuity, I have to be able to trace this graph without ever lifting up my pencil. So there's a nice example of, we didn't actually have a function. What we had was all the information that a function can generate for us, and then we created the function. So it's kind of, choose your own adventure, choose your own function. Your function might look a little different. Maybe your curves aren't as wide or wider, or, whatever it is. As long as it meets all the criteria, then it fits these conditions. Okay. So let's take a look at, there's one more property that one more test that I want to project up here and get into your notes for this chapter. And then I want to do another example where we actually start with a function. I want to look at a trig function and talk about where it's increasing, decreasing, and has intervals of concave up, concave down, and inflection points. So here's one more test that we want to make sure that we go through in this section, and it is called the second derivative test. And what it is useful for is if we have calculated the first derivative, we figured out all the critical points from the first derivative where we're increasing, decreasing, we've taken the second derivative, figured out where we're concave up and concave down. This test can be useful to determine where the local maxes and minimum values are, or the relative max and min values of a function. So it is a pretty specific test. First it says that we have to have a continuous second derivative near a point. Then if at that point we know that we have a horizontal tangent line, meaning that the derivative at that point, the first derivative at that point is equal to 0. So we know we have a horizontal tangent line, and we know that the second derivative is greater than 0. We are concave up. So if we have a horizontal tangent line and we're concave up, that is going to tell us that we must have, at this point right here, we must have, that's the scenario on the graph where I'm drawing now, that we must have at this point with that horizontal tangent line concave up, it must be a local minimum. Okay? So if we know that we have a horizontal tangent and we have concave up, the concavity is up at that point, then it must be a local minimum. And the opposite, if we know that we have, same condition to start with, we know that we have a horizontal tangent at a point. So right here at this point on the graph, we've got a horizontal tangent, but rather than being concave up, if we're concave down at that point, that must be a maximum. We must have a local maximum. So if we're concave down, then we must have that local maximum at that point. So it's kind of a nice, it's just a nice test if we have all of the information already, if we've already figured out where we're concave up, concave down, where we've got those first order critical points from the first derivative where we have the horizontal tangents, then intuitively it should make sense. If you have a horizontal tangent, just kind of think about it. If you've got a horizontal tangent and you know the concavity, then you can quickly look at this and say, oh, at this horizontal tangent, we're concave down, so that must be a max. Concave up at this horizontal, that must be a min, a max, and a min as we kind of follow it through. So it gives us just kind of a nice, it brings together both our first and our second derivative information about horizontal tangents and concavity, and intuitively puts them together as you would expect. So called the second derivative test, worth making sure we put down in our notes because it's a handy little test to have in your toolbox of math tools. All right. So I want to go through one more example on this video where we go through the entire process from start to finish. So we are going to take a look at a function, and this one is going to be a trig function. See if I can get the instructions all on the screen here. We're going to find the intervals of increase, decrease, and the intervals where we're concave up and concave down. So remember to find the intervals of increase, decrease. That's going to be utilizing our first derivative. So we need to know the sign of f prime of x, and then to find the intervals of where we're concave up, concave down, we're going to be taking a look at the sign of the second derivative. I used f of x here. It's actually defined as y, but we could think of it as f of x. And then we're going to determine all the local maxes and mins. Once we have those two sign charts, we'll be able to do that, and the inflection points, so the places where the concavity changes as well as where we have a local max or minimum value. And then at the end, I want to find a rough sketch of the graph. Once we have all that information is useful, but what do we do with it? Well, we would primarily use it to graph a function, okay? Unless we have context, and then we could use it to answer questions like where is the profit at a maximum or something of that nature. Okay. Also, something to consider here is a restricted domain. So this is obviously a function, as we've got this trig function in it. We're going to have some cyclical nature. Something is going to be happening here where we probably have some cyclical nature, and this goes on and on forever. The domain of this function is actually, without that restriction, the domain of this function would actually be from negative infinity to infinity. Which would be an interesting scenario to look at, but that might take more time than if we have this restricted domain. Plus, if we have the restricted domain, we can even, I didn't ask it, but we could even talk about absolute maxes and mins, because we do have a continuous function on a closed interval. So if we have time here at the end, we might even consider that. Okay, before I jump into this function, just a quick projection. I pulled them from the notes earlier and put them right here, is just a quick reminder of our first derivative test. So the process that we're going to use is we're going to find all the critical points. So the first thing we're going to do is find critical points of the first derivative. Then we're going to make a sign chart of that first derivative, and we're going to use that to determine where we have our local maxes and mins, as well as state our intervals of increase, decrease. So that's the process that we're going to start with, using that first derivative test to figure out where we increase and decrease. So let's go ahead and do that. So to find where we increase and decrease, we're going to use the first derivative test. And we need the first derivative to do that. So that's going to be 1 minus 2 cosine of x. And then we're going to find the critical points. And I am abbreviating here CP for critical points. So we're going to find the critical points. So as a reminder, critical points are when the derivative, we have actually y here instead of f of x. So I'll say when y prime is equal to 0, or when y prime is undefined. Now, for this particular function, we have 1 minus 2 cosine of x. This is defined on all reals, from negative infinity to infinity. It is just a trig function. It's a shifted trig function, and not just any trig function. It's the cosine. Therefore, it has a domain that is all reals. Okay? So it is never undefined. Okay, so undefined, never. I just tend to put a little cross through that. I don't have to consider that case. Well, I mean, I did consider that case, but I don't have to do any work on that case because the function is always defined. When I say the function, I'm talking about the derivative. It turns out actually the function itself is also defined. But where would it be equal to 0? That's where we're going to need to do a little bit of work. So when does y prime, which is 1 minus 2 cosine of x, equals 0? So that would be when minus 2 cosine of x equals negative 1. When the cosine of x is equal to 1/2. So when does that happen? Well, the cosine is equal to 1/2 at pi over 3 in one period, at pi over 3 and at 5 pi over 3. Now, also, that happens every time we cycle through a period of the cosine. So at to each of these, we would add 2 pi k, where k is in the integers. Okay, so where k is an integer. Now, we have that restricted domain. So I just solved this across the entire number line, but where would those points occur on the domain? So then we consider on the restricted domain, which was from 0 to 2 pi. So which of these points is in the interval from 0 to 2 pi, right? Because this continues. Like you've got your pi over 3, your 5 pi over 3, and then you take pi over 3 and you add 2 pi k. So then you'd be at 7 pi over 3. And we'd keep going, but that would have bumped us out of that 0 to 2 pi range. So on the restricted domain, the 2 points we need to look at, the critical points that we have on the restricted domain are pi over 3 and 5 pi over 3. So we're going to use those now to create our sign chart. So now our second step is create that sign chart. So in some previous examples, our sign chart went all the way from negative infinity to infinity. But this sign chart, and again, remember this is like a little snippet. It's just the horizontal axis from the rectangular coordinate system if we were to be graphing this function. So we're looking at the x-axis. We are only looking at it from 0 to 2 pi, because that's the restricted domain. So, even though this function does go across the entire number line, we are only looking at it on this little portion from 0 to 2 pi. On that portion, we put in our critical points. So we've got pi over 3 and 5 pi over 3. We are looking for the sign of the derivative, sign of y prime. We'll put the signs on the top of this number line, and on the bottom we'll discuss whether y is increasing or decreasing. So that's the information that's going to come out of this sign chart. So all we have to do now is pick some numbers between 0 and pi over 3. So we'll pick some test points. So up here we're picking some test points in red, and let's see, something between 0 and pi over 3, like pi over 4 would be a good one. And I'm picking one that I can actually plug into I've actually lost my derivative. It's way up here. So let's rewrite our derivative down here so we have it to look at. So we're creating a sign chart for y prime equals 1 minus 2 cosine of x. So if I pick pi over 4 and I plug pi over 4 into that, and again, I'm just looking for the sign here, but if I plug pi over 4 into that derivative, then y prime becomes 1 minus 2 times root 2 over 2, which is just 1 minus root 2. Okay? So I'm going to write that down right there so that you can see that. But I know that root 2 is larger than 1. So if I take 1 and I subtract root 2, and I'm not even going to go to a calculator. I don't need to do a calculator for this. I can do it in exact form and do it pretty quickly just to find the signs. Again, remember, we are only looking at the sign. We don't really care about the value on this interval at our test point, just what is the sign, because that's going to tell me if I know the sign of the derivative, it's going to tell me if the function is increasing or decreasing. So if I take 1 minus root 2 being a little bigger than 1, that's going to give me a negative. So I know that the sign of the derivative here is negative, which means that we are decreasing on this interval. Then I pick a test point between pi over 3 and 5 pi over 3, and I'm strategically picking ones that'll be easy to do my test points at. So I'm going to pick pi over 2. Okay? So I grab pi over 2, plug that in, and I get 1 minus 0. Of course, that is 1, so that is going to be positive. Okay? Cosine of pi over 2 is 0. And then I'm going to pick something like 7 pi over 4 on this last interval. Oops, I forgot to write increase. That means we're increasing across that entire interval from pi over 3 to 5 pi over 3. Then I pick something like 7 pi over 4. If I plug in 7 pi over 4, it's actually going to be the same as what we had at pi over 4. 1 minus 2, the cosine of 7 pi over 4 is positive root 2 over 2. On that interval, so I end up with 1 minus root 2 here, and that of course is negative. So we are decreasing again on that interval. And so right now what I have is I also know at these 2 points at pi over 3 and at 5 pi over 3, those were horizontal tangents. Y prime was equal to 0, which means, and I'm going to just abbreviate this, put whatever notation you want. I like to say HT for horizontal tangent, but I also like to indicate that the derivative was 0 under those points. So I know that at these 2 points I have horizontal tangents. Right? Remember, our critical points could be points that are restricted from the domain, or they could be where the derivative is undefined, or they could be, in this case, of course, just our derivative is equal to 0, a horizontal tangent. So it's worth noting what those points are on the sign chart. Okay, now we actually have, so we can even start to get our rough sketch right now, and we see here that we're decreasing. So we start off and we decrease till we get to a horizontal tangent. Okay, at a horizontal tangent, you would have, horizontal tangent line. And then we start to increase, and we increase all the way. Oh, I didn't even give myself enough space here. So I spread this out pretty far. So we're decreasing, hit that horizontal tangent, start to increase till we get to a horizontal tangent over here. I did not give myself much space that second time either. And then we start to decrease again. So that's going to make these 2 points local maxes or mins. We just have to figure out which they are. Well, this is clearly, if we decrease then increase, this is clearly a minimum, and if we increase and then decrease, this is clearly a maximum. So we get that general shape of the graph, and we can see that max and that min. So now we have everything we need out of this sign chart to give a little summary, and so that step that I just did right there was we found maxes and mins. That's the third step out of our sign chart, our first derivative test here. So now we're just going to put all this together and we're going to state the summary. And so the summary here is going to say that we are increasing. So let's state intervals of increase. So we are increasing on the interval from pi over 3 to 5 pi over 3. And then where are we decreasing? So let's state our intervals of decrease here. So we have our two intervals of decrease. We are decreasing from 0 to pi over 3, and then we're decreasing again from 5 pi over 3 to 2 pi. And we can see that we're pulling that right out of, pulling that right off of the sign chart. And then we can talk about the local max min values and the local max and min values we have at x equals pi over 3, we have a minimum, and at x equals 5 pi over 3, we have a maximum. Now, I am going to plug those into the function, but I'm going to do that at the end after we've gone through the second derivative and identified inflection points as well, because I would like to organize this in a table. When I go back to plug, right, we're going to need to plug those back into the original function to figure out what those actual ordered pairs are, because this is an ordered pair, pi over 3, comma, right, we don't know yet, and 5 pi over 3, we don't know yet. I'm going to plug that back into the original function, but I'm going to do that at the very end. I'm going to make a table with all of my output values to help me with the graph. So we'll come back to those. Right now we've identified where they are in terms of their x values, and then we'll come back and plug those into the y values. So there is my first set of information out of the first derivative. Now what I need to do is I need to go and take a look at the second derivative. So we found the first derivative. Now we're going to do real similar, and we're going to plug into the second derivative. So for the second derivative, to figure out concavity, let's just remind ourselves here of that process. So for the second derivative, we're going to first of all, take the second derivative and then figure out where all those second order critical points are. So we're going to figure out where the second derivative is 0 or undefined. Then we're going to create a sign chart for the second derivative and then use that sign chart after we have it and know where the second derivative is changing from concave up to concave, changing sign, which is creating a change from concavity in the function, then we'll know where the inflection points are. So it's a real similar process to what we just did, but because we're using the second derivative, it's giving us information about concavity of the function and where the inflection points, the changes in concavity, are on the function. So let's go ahead and do that. And I'm going to, let's just do it right next to it here. So we've got our first derivative. Let's go ahead and a little bit over here so we have some space, take the second derivative. So the second derivative of this function, our function itself was x minus 2 sine of x. Our first derivative was 1 minus 2 cosine of x. And our second derivative, the 1 is going to become 0, and then the derivative of cosine is negative sine, so this becomes positive 2 sine of x. So we've got all of our derivatives here. And now we're going to find the critical points. So we're going to find the second order critical points, which is when y double prime equals 0 or when y double prime is undefined. Again, this function that we're looking at is a trig function. So it will never, it's a trig, not only is it a trig function, but it's a sine or cosine, which are defined across the entire number line. So this has a domain of all reals. So it's always defined. So there's no points where it's undefined. That's funny, I wrote defined, but I meant to say undefined. So there's no points where it's not defined. So what we need to figure out is when is it equal to 0. So when does y double prime 2 sine of x equal 0? Well, that's going to happen when the sine of x is equal to 0, or when x is equal to any multiple of pi, okay? Where pi is an element of the integers. So it's going to happen when you have any multiple of pi. So now we're looking at all of those possibilities. Well, again, though, we're on this restricted domain. So on the restricted domain, which was just from 0 to 2 pi. So remembering that we had that restricted domain. So on that restricted domain, we are looking at just x equals pi. So x equals pi is the only critical point, the critical point on that restricted domain, second order critical point. The second order critical point on that restricted domain is just at pi. Okay, I'm running into my work down below, so I'll scoot over just a little bit. Now my second step now is going to be to set up the sign chart for the second derivative. So we're looking at a sign chart for the second derivative, create our sign chart. Again, we have a restricted domain, so we're only looking at it from 0 to 2 pi. And we had just that one critical point that falls in that interval, so we put pi on there. We are looking at the sign of the second derivative, and it's going to tell us about the concavity. It's going to tell us where y is concave up or down. Okay? So we're going to pick values. Where is y double prime? Y double prime was equal to 2 sine of x. So let's just get that down here. I know that was up above. So let's get that there so that we can look at the signs. So now what we're going to do is we're just plugging in values. So, you know, like pick your little test points, just like we did for y prime. Pick your test points. You know, obviously pi over 2 would be a quick and easy one to do. Plug in pi over 2, of course, that's going to be 2. So that's positive here, which means we're concave up. And then maybe 3 pi over 2. You know, just pick easy ones. Plugging in 3 pi over 2 here, of course, you get negative 2. So that would be negative, and that would be concave down. Okay, so we're concave up. Concave up has this sort of shape. Concave down has this sort of shape. Okay, where we're concave up, we're sitting on top of our tangent lines. Concave down, we're hanging from our tangent lines, which makes this point right here an inflection point, an IP. So now we have all of that information. That was step 3 that we just did. We identified the inflection points. So identifying the inflection points is anywhere you have a change in concavity and the function is defined. That is an inflection point. So now we can summarize all of this just like we did here. We knew where the intervals of increase, decrease were and the local maxes and mins. We can do the same thing here. So we can say, okay, intervals of concave up. Well, we're concave up from 0 to pi and concave down from pi to 2 pi. This is on that restricted interval. Then we also have inflection points, and I abbreviate inflection points just IP. So inflection points, and we actually only have one, and that is at x equals pi. So x equals pi is an inflection point. So we have all of this information now. So we've got our intervals of concavity, we've got our inflection points, we've got our local maxes and our mins. So all kinds of information about this function now. And we could go to giving a rough sketch of this function, but to do that, it would be useful to also know what the actual ordered pairs are at those interesting points, those maxes and mins, and at those inflection points. So the last thing I'm going to do here before we get a little graph is I'm actually going to take all that information and I'm going to create a table here with ordered pairs. So I'm going to create a little table of ordered pairs here just to make it really easy and simple to graph, because if I have some ordered pairs and then I can just fill in with all the information that I have, we'll have a really good graph actually. So remember that y was x, what was y? Y was x minus 2 sine of x. And what I'm going to do here is I'm going to fill in I'm going to start with my two endpoints, 0 and 2 pi. Those were the endpoints because I had an interval that I was looking at. So that's an endpoint, start endpoint, and end endpoint. Okay, so where our A and our B essentially of the closed interval we're looking at. And then the other points that were interesting were pi over 3, pi, and 5 pi over 3. And that came from all of our work with the first and the second derivative. We have already identified that pi over 3 is a minimum. We've identified that pi is an inflection point, and we've identified that 5 pi over 3 is a maximum. So we've identified all of those points. And so I'm just going to plug those right into the function, and we'll see what we get. And just because the video is getting a little long here, I'm going to go pretty quickly through this. So this is 0, plugging pi over 3 into that function. The exact value is pi over 3 minus root 3, but that's approximately negative 0.69. Plugging in pi, you get back just pi, which of course is just approximately 3.14. Plugging in 5 pi over 3, you get 5 pi over 3, excuse me, plus root 3, which is approximately 6.97. Plugging in 2 pi, you get back just 2 pi, which is approximately 6.28. So we have all of those values. We've identified each of those ordered pairs as maxes or mins, and we can take all of this information and we can get a pretty nice little graph. And I'm just going to sketch it out really quickly here. But taking all that information about this function, let's see if I can get it all on the screen here. I can create a pretty quick little graph of this function that will be pretty accurate. So let's say that's 0, that's 2 pi, here's pi over 3, here's 5 pi over 3. And we start at 0, 0, and then we drop down to a little bit below the x-axis. This was pi over 3, but I'll move it over just a little bit. Pi over 3, so we drop down here at pi. We're up here at pi. And then at 5 pi over 3, we're up here. And at 2 pi, we've dropped just a little bit. So I'm not giving it exactly to scale, but it is relative based on those points that I found. Concave up, increasing till 5 pi over 3, concave down, and we've identified a pretty good sketch where we've got our min, inflection point, max, and these were the two endpoints of the interval. And we can get that pretty nice sketch from all that information. Like, we have just done a ton of work to really get into that function and see what all of that is about. So let me move this guy. This is an example we'll do in a separate video. And so we have all that information about the graph giving us in the end, this nice little graph where we've summarized all that information. See if I can get it all on the screen right there. So it's quite a process. And for that example, I wanted to do an example where we went through it all at once for a function and even on a restricted domain. So we could talk about looking at just the points that are on that restricted domain. But that's the process, and look at all that information that we were able to get from the graph. And so make sure that you follow through this, and when you're doing these problems that you take your time and you really, you follow the process, take the time, look at where those first and second order critical points are and what that then can tell us in a sign chart about increase, decrease, and concavity.